This video is just the basics about electronic components, what they look like and what they actually do, and how they work in fact. So let's start with one of the most common, the one that I just picked up there, the resistor. So this is a 1000 ohm resistor. I can tell that from the colour bands on it, and we'll look at that later on, how the colour bands are interpreted. However, the function of a resistor, if I use the water analogy, because the water analogy is very good. If you have a pipe with water flowing through it, and part of that pipe is narrowed down to a section, then that will restrict the flow of water through that pipe. Say for instance the main water pipe came into the house, if you put a very thin pipe in line with that, even a fairly short one, then it would really restrict the flow of water coming in, because the water would want to flow through quite quickly, but it would be forced in through this narrow channel, and the resistance posed by that narrow channel would limit the water flow in the same way that a resistor does exactly the same to electricity. It limits the flow of electricity, the flow of current. And in this case, with the water analogy, the pressure of the water equals the voltage. And it's quite interesting that the Chinese sometimes refer to the voltage as pressure, and that's exactly what it is. And the flow of the water equals the current. So the higher the flow, the higher the current. Now the construction of a resistor is usually, in the case of these ones, this is a carbon film resistor. And you get metal film, carbon film, wire wound, but one of the most common is just carbon film or the metal film. And they have a little ceramic tube which is coated with either the metallized coating or a carbon coating up to a specific thickness. And the thicker the carbon coating on it and the type of the composition they're putting on it, the more conductive it will be. But then they can fine tune that. They actually cut a spiral around it, and that creates a long thin path of the carbon, and that increases the value of the resistance. And once they've done that, they put a metal cap in the end with the leads coming off, and they dip it in a sort of I suppose it's a lacquer really. And typically with the carbon film resistors, which are my favourite, they're one of the easiest to read, it'll be this sort of beigey coloured, I'm not sure, what would you call that colour? I've never really thought about that. Beige, let's call it beige, it's sort of rich beige. And the metal film resistors, which I don't like, because they're usually blue, and they're really hard to read. The blue colour makes the colour bands, makes it easy to mix like colours like orange and brown, because they've got such a dark background. But I'll go into those colours afterwards. So that's the function of a resistor. I'm not going to go into it too much at the moment, because at the end of the video I'll cover things like Ohm's law, but I don't want to bore the pants off you, so let's move on to capacitors. Oh, I should continue and say about the resistors. The function of a resistor is to limit the current flow. So say for instance you had an LED, you wanted an LED to light from a battery. If you connected the LED straight across the battery, it would burn the LED out in most instances. But if you put a resistor in series with let's just draw it as a physical LED, and you hook it across the plus 12 volts, and 0 volts, then by choosing the resistor value you can actually limit the current to the correct value for the LED. They're also used for things like time delays. You might have a resistor charging up a capacitor, you know, it trickles the current into it until the voltage reaches a certain level, and then that could be used as a timing function. And you also get variable resistors where effectively it's a carbon track connected at both ends. You only really need to use it connect at one end, and with a wiper that actually wipes round that track, so that, you know, depending on its position, that will vary the resistance. So let's move on to capacitors now, because they're quite interesting. So a capacitor, in its most basic form, is a layer of insulating material with a conductive surface on each side. And the best way to describe a capacitor in the water flow theory is a chamber with a diaphragm in it that stops the water flowing directly through. And that diaphragm can flex a certain amount in either direction. So if, say for instance, you connect it across a battery, the positive charge would flow in at this side and it would cause it to flex over to the negative side. It doesn't actually physically work like this, but this is a good way to describe it. And if you reverse the polarity then, that charge, that amount that had filled up would then be pushed out the other side and it would flex the other way. And this allows, capacitors can be used to basically hold a charge of electricity, or in the case of the AC capacitors, that you often see me using these in my LED lamps, that diaphragm, it means that on the AC, on each half wave when the polarity swaps, that will let through a small amount of energy. The sort of electrons will flow backwards and forwards through it, but not just pass right through like a sort of short circuit. So to describe the capacitor, to actually show you what a capacitor does, let's make one. So I've got a bit of a cardboard here. This is a standard 6x4 photo piece of photo material. And I've got 2 bits of metallized film. So let's stick the metallized film on either side. So we've got a metal electrode and I'm sticking it onto the insulator, the dielectric. And this is old aluminium tape, I think, because it doesn't seem to stick very well. But that's alright, it'll do what we need to do. And then the other side of this, I'll stick the other bit of tape, and that's the other electrode. And this is the physical construction that's used throughout all capacitors. They're all pretty much like this, but not using cardboard and aluminium foil. So let's get that pretty much as close to the other one alignment as possible. And the 2 factors determining the capacitance here are the area of metallization that's in parallel with the other one, and how thick the insulator is in between. And you'd think, you know, this card, it's very thin, so it's going to be quite it's going to be a modestly high value of capacitance, but that's not true. This is not going to be a high value of capacitance at all. So let's put this round, let's be optimistic and say 200 nanofarad. And I'll connect it one side and the other side. And the capacitance is actually, I'm actually connecting onto the adhesive side here. My capacitor measures oh that's terrible, isn't it? It's 1.8 nanofarad, it's not very high at all. And if I was to cut this in half, so the actual, to prove that the area of the foil affects the capacitance, if I get a pair of scissors, and I cut this in half right now, so it's 1.83, if I cut that in half, it's half the capacitance, it's now 0.8, and if I cut that again in half, it'll go down to about 0.4, which it has. So that's basically how a capacitor works. It's basically an insulator, the 2 metal plates on either side, and the area of the metallization and the thinness of the separator is what determines the capacitance. And to get the value of capacitance up, that means that in reality, for components like this little 100, keep in mind that I managed, what was that, just a couple of nanofarad? This one is rated 100 nanofarad. And if you look at things like this is an electrolytic capacitor which is rated 470 microfarad, which is a massive capacitance. And to achieve that, let's get the notepad back in again. To achieve the higher capacitance, they often make the capacitors multi-layer. So this is something I just printed out, designed it on the computer for the printed circuit board design sort of layout, but I just did it as a sort of graphic. And if you can imagine that the blue is layers of insulation in the ceramic capacitors, and these are metallized sort of plates, then by alternating the pole, sort of creating a sort of comb of them with insulators, and then putting a metallization down the end to connect them all together, you can create quite a large capacitance in a small area just by making it a multi-story capacitor, so to speak. And that's still the layers of insulation in these, it's still going to be super thin. You'd need a microscope probably to see all the layers. Where you're going for a high voltage capacitor, the size has to go up. These are also 100 nanofarad. So you look at this one, it's 100 nanofarad, it's really small, but it's a low voltage one. when you're increasing the voltage, you have to increase the thickness of the dielectric, the insulation between them. And to make this type of capacitor, these are metallized film capacitors, and it's a film that's metallized on one side. And they take two strips of it and they basically sandwich them together. And the plastic aspect of it is the insulator, and the metallization is the electrode. And they, to fit a lot in a small area, they then actually just spiral. They take a big long strip and they spiral it round into a small area, and that's what creates the sort of larger area. And the thickness of the plastic film itself will determine the voltage rating. This is a ceramic disc capacitor, usually quite low values. It's usually one of the simplest, and it usually is just a disc of ceramic with a conductive layer on both sides, and then an electrode that just comes across and comes off, and then it's dipped in insulation. But when you think that even this one is rated 10 nanofarad, and it's rated 1000 volts, but to get that 10 nanofarad, the insulation must be really, really thin inside that. I've never actually opened one of these up. Let's open one of them up right now and take a look. Oh, not this thing to do with your snips. Oh, that is so... it really is wafer thin in there. It's so thin that most of the thickness of that is the protective coating. That is super thin in there.